Geometry Lesson 2.3a, we'll be talking about area in relation to sine. To begin, I just want you to know that this is a difficult section. You need to take notes, you need to draw pictures. So I will let you know that we will be collecting in class your notes and your pictures for the examples and from this slide. So let's begin. The tangent function can be used to solve the area of a regular polygon if the side lengths are known. If you remember, the formula for area of a regular polygon is 1/2 AP. Sometimes you don't have all the information, so we're going to do a little bit of review to remind you what we've learned in the past, and then solve some of that information using trig ratios. So the first thing we're going to review is the measure of a central angle of a regular polygon. So you should have this formula written out. It's basically 360 divided by the number of sides will equal the central angle. In the case of a regular octagon, it would be 360 divided by 8 equals 45 degrees. We need to also remember that radii are congruent. So the triangles formed by a central angle and its intercepted side are all isosceles triangles. Let's take a look at that. So here we have an octagon. We've drawn our central angles and our radii, which have divided this octagon into 8 isosceles triangles. So that means for this triangle PAB, you have PA and PB, which are congruent. Now the apothem for this triangle PAB is both a perpendicular bisector of the side, so it bisects AB, and of the central angle, so it also bisects the central angle. And I want you to make sure that you have that on your drawing. So be sure to make a drawing of this, and you should have the two angles marked, congruent, and your bisected sides congruent right here. Then you should redraw the triangle. So PAQ is now divided into two congruent right triangles, and the one we're going to redraw will be PQB. So you need to redraw PQB. You'll have the apothem written on the side there, and the side length will be half of the total length. So all of the side lengths in this octagon will be 12, so half of 12 will be 6. So you'll have the 6 centimeters, and we know that the central angle will be 360 divided by 8, which is 45, and I have that right here, and that QPB will be 1/2 of that. This whole angle here is 45. Each one of these is 45 degrees. So half of one of those angles is 22.5. Now what you do, now that you have all of your information, you'll solve first for the apothem. So you're going to solve for the apothem. And to solve for the apothem, this is a right triangle. And this right triangle, this side here, is part of one of the acute angles. Remember, you have P right here, and we know its degrees. We know that P is 22.5 degrees. So we'll take P and we'll be solving for what information we have. Well, we have opposite over adjacent on the sides. Opposite over adjacent is tan. So tan of the angle 22.5 equals 6 over A, the A being the apothem. However, the A is also adjacent, and this is done on purpose. This is so these formulas will tie together. Now we need to solve for the apothem, A, and that means that we're going to be solving for our A in our formula, and right here it's dividing 6, so we need to multiply both sides by A. We'll end up with A tan 22.5 equals 6. So A tan 22.5 equals 6, and that's by multiplying both sides by A. And now we need to solve for just A, the apothem. So what we'll do is divide both sides by tan 22.5, and that leaves us 6 divided by tan 22.5, which is approximately 14.5 centimeters. So we now know what our side length is, and we're going to use that to solve for area, which is the original intent of the problem. So we have our original formula. Area equals 1/2 AP. So 1/2 AP. We have 1/2, and the apothem. Now we could put 14.5 in here, however it's approximate. So let's go for what's more precise and substitute the 6 divided by tan 22.5 for apothem, and then we'll multiply that by the perimeter. The perimeter is 8 sides times the length of 12, and that becomes approximately 695.3 centimeters squared. Now I realize that's a lot of steps, but if you take one piece of paper and you write that example I just showed you in your notes all in one page with every step I just gave you, so you should go back and run the video again and be sure to fill in each step in what you're solving for. It should be no problem. It's not new information. It's all repeat information with the exception of using tan for the apothem. Let's look at example 1. And in example 1, we're going to find the area enclosed by the pentagon near Washington, D.C., and we're going to solve to the nearest of the 1/10 of an acre if each outer wall is 921 feet long and 1 acre equals 43,560 feet squared. So do not let this throw you because it's a word problem. Make your sketch. It will ask you on every problem in this unit to make a sketch. You need to do this. So we're going to find an area enclosed by a pentagon. Now the pentagon in Washington just happens to be in the shape of a pentagon, so draw it. And then it says each outer wall is 921 feet long. So go ahead and mark that on your drawing. Now, each central angle is going to measure 360 divided by 5 side lengths, which is 72 degrees. So this is 360 divided by the 5 sides of the pentagon. So each central angle will equal 72 degrees, and it's here in the drawing. Now we need to drop our altitude, which is also our apothem. So we're going to drop this altitude. We're going to create 2 congruent right triangles, and we now have A that we need to solve for, and we know that we have a side length here that will be half the original. So the measure of Q PB will equal 1/2 of the central angle. So it's 1/2 of a central angle of 72, which is 36 degrees. And our side length will be 1/2 of the total side length AB, which is going to be 1/2 of 921, which is 460.5 feet. So this is exactly like the previous example I showed you. Now we're going to apply the tan ratio to solve for the apothem. So this will be tan, and it'll be 36 degrees. So we're talking about this angle right here, 36 degrees. So tan 36 will equal 460.5, which is opposite, and then divided by A, which is adjacent. So there's your tan formula. We're going to multiply both sides by A, and then we're going to divide both sides by tan 36 degrees. And then here is your apothem. So let's substitute that into our area formula, and we have 1/2 of the apothem times the perimeter, which is 5 sides, times 921, a length of 921, and that's approximately 1,459,379 feet squared. Now, one of the things they did throw in here, it says convert to acres. They gave you the ratio of 1 acre equals 43,560 feet. That's exactly how you write it in your conversion formula. 1 acre is to 43,560 feet squared. We now can cross off feet squared, and we can divide the 1,459,379 by 43,560, and we'll get approximately 33.5 acres. So there's your problem. Yes, it is a few steps, but it's all on one page here. So if you want to copy that page also, that will help you when you're doing our problems that are coming up. So we can also find the height of a triangle when the side lengths and measure of the included angle are known. So let's look at this triangle. We have MNO. We need to solve for the height. We have one side length of 10 inches and a side length of 15 inches that has an included angle of 40 degrees. So as long as we have an included angle in between two side lengths, we can solve. The altitude from angle N divides MNO into triangle MNO into two right triangles. So we're familiar with this. We know how this works. Now these triangles are not congruent. They're just divided using the properties we know about altitudes with right triangles. The hypotenuse and an acute angle of one right triangle is known, so we can apply the sine ratio. We have the sine of angle M, which is 40 degrees, we know, and we have the opposite we need to solve for, and we have the hypotenuse. So opposite over hypotenuse is sine, so here we go. Sine 40 degrees equals the h from height over the 10 inches, and we multiply both sides by 10. 10 sine 40 degrees is approximately 6.4 inches. And that's all you have to do with that problem because you were finding the height. Now we can also find the area of a triangle using a sine ratio. This is the same triangle. So once you've found the height, you can now solve for your area. So the area will be 1/2 the base, which is 15 inches. And you remember, you don't use the smaller triangles. Now you're back to the larger triangle. So it's 1/2 15 inches. And we're using the height that we found on the last slide. So the height is 10 sine 40, which will equal approximately 48.2 inches squared. So when we first began this unit, I told you if you have missing lengths, we can use we can use trig formulas, trig ratios, to find missing sides also. Let's take a look at example 2. We have a triangular lot. It has sides of 80, 90, and 110 feet. It has an angle between two of these sides. It's included of 46 degrees. So we have an angle of 46 degrees. We need to solve for the area of the triangle, but we do not have the height. So let's apply the sine ratio to find the height. So sine of 46 will be the opposite, which is h, over hypotenuse, which is 90. And multiply both sides by 90, and you get h equals 90 sine 46 degrees. So, 90 sine 46 degrees will be our height, and we can now substitute that into our formula. So we have 1/2 base times height, which is approximately 3,560.7 feet squared. If you're having difficulty multiplying your sine ratios with your regular numbers, remember to work parentheses first. Do the sine ratio, or do your 90 sine 46 first, then multiply it by 110, and then divide by 2. And the last formula, that formula that you just did can also be derived to become another formula. And the formula for an area of a triangle in terms of two sides and an included angle using sine, if CB and the measure of angle A are known in ABC, then sine A equals H equals C sine A. And that was what you were finding on the previous slide. You can take that C sine A, so C is this side. You're taking the sine of that and doing A, which would be this angle A, whatever the degrees are. You sub it into 1/2 BH. So now your formula becomes 1/2 B times the height, which is C sine A. And if you use your algebra to derive that formula and make it, I'm not sure it makes it easier, but you can restate it. It becomes 1/2 BC sine A. Using similar logic, you can also state that the area equals 1/2 AC sine B, or 1/2 AB sine C. Now, what does this mean? Well, this means that you may have different angles that you're using in this triangle that you'll be finding sine for. Whatever angle you have, you will be using your opposite over your hypotenuse. So this is what the formula will look like. We have two theorems coming up. If you take a look at this triangle, this is your standard triangle where we have A, B, C, and then the opposite sides are small a, small b, small c. In theorem 12.3.1, the area of a triangle is equal to half the product of two sides and the sine of the included angle. We already know that the area of a triangle is equal to 1/2 the product of two sides. And let me correct this. This is basically a restating of the last slide where we used similar logic, and this is the formula that comes, the theorem that comes from that formula. So A equals 1/2 BC sine A, or 1/2 AC sine B, or 1/2 AB sine C. And then we have theorem 12.3.2. This is also one of Heron's formulas. It's called the side area theorem. And the area of a triangle with side lengths A, B, and C is given by, and this is the actual formula, it's the square root of a side length times side minus side A times side minus side B times side minus side C. A little confusing, but this formula is just another formula you can use. It's called the semi-perimeter. And the semi-perimeter would be 1/2 A plus B plus C. So essentially, way back, Heron stated that you could take the perimeter of a triangle, ABC, and using side, you can divide it in half and you will get 1/2 of side. So they'll have you solve a few problems, but this is very basic, very easy to do. So your homework is numbers 1 through 12, and I'm going to give you some helps. Homework problems 1 and 2. In number 2, you're asked which equation is used to find the value of x. So we're looking for the hypotenuse here, and all they're asking you is to check out what information you have and find what trig ratio is correct. So we have an acute angle of 36 degrees, and we have values for opposite, which would be 10, and adjacent. So opposite over adjacent is tan. Now remember, we won't use the hypotenuse to solve these, so we're not saying x over something. So opposite over adjacent, tan 36 equals 10y, and that was answer C. So that's how they want you to solve numbers 1 and 2. In numbers 3 and 4, they're just asking you which equation is true if tan 22.5 degrees equals W divided by 12. Well, if I restate that, tan 22.5 equals W divided by 12, all I have to do is find what W equals to line it up with the answers you're given, multiply both sides by 12, and we have 12 tan 22.5 equals W, and that is answer A in your text. So do the same thing with number 3. Homework problem number 6 uses Heron's formula. So it just asks find the semi-perimeter of each triangle with given side lengths. So you plug those side lengths into the formula, and we have 15 plus 15 plus 15 divided by 1/2, which is 22.5. Do the same for number 5. Now homework problems 7 through 12 are just like example 1. 7 through 9 are actually exactly like example 1 because they have a pentagon to compare it to. Numbers 10 through 12 are similar, but you'll be using an octagon, not pentagon. So everywhere you had the 5 for the pentagon, you're now going to have the 8 for the octagon. So if you made good notes for those 2 examples that I gave you, example 1 and the problem right before it, then you will be able to go ahead and do these. Be sure to give me a call if you have difficulty, and we'll be moving on to some more problems in 12.3b.